Example 4, part 1, we want to sketch the graph fx is equals to x squared minus 6x plus 7. So we might think at first that this is actually factorizable, but in reality, it's actually not. So if we check this out, right, if fx is equals to x squared minus 6x plus 7, take note that because of the plus 7, we can't say that this is equals to x minus 7 times x plus 1, which will give us negative 6x, but it doesn't give us the plus 7. So in this case, the best way of sketching this is to actually complete the square. Alternatively, we could approach this by using the quadratic formula to solve for x-intercepts, but then we have to go out of our way to find the vertex anyway, whereas if I complete the square, it will give us the vertex straight away, and it makes this equation a little bit easier to solve for the x-intercepts as well. So if we look at this expression, right, and we just focus on the x squared minus 6x, we know that to make this a perfect square, we need x squared minus 6x plus 9. The plus 9 comes from taking the minus 6, dividing it by 2, and then squaring it. So then I've got the plus 7 at the back, and then our minus 9 to compensate for the plus 9 inside the bracket. So what this becomes is x minus 3 all squared minus 2. So this tells us that the vertex of this parabola is therefore at 3, negative 2. So if I set up the Cartesian plane, okay, so I've got an x-axis and I've also got a y-axis, right? So let's say we've got something that looks like this. So this is y, origin, and x. So 3, negative 2 is, let's say, going to be somewhere over here. The y-intercept is actually positive 7, so that's actually going to be all the way up here. So what that implies is that even though we don't have the x-intercepts, we know that both x-intercepts are going to be positive. This is a concave up parabola, so joining everything through, we're just going to get something that looks like this. Okay, so this is essentially what fx looks like. So the y-intercept up here is 7. This is not drawn to scale at all. The vertex is 3, negative 2. And if we want to go the extra mile to find the x-intercepts, okay, so let's say we let y is equals to 0 for x-intercepts. Then what we've got is x minus 3 squared minus 2 is equals to 0. Okay, this is going to be the easiest form to solve. Move the 2 to the other side. So we've got x minus 3 squared is equals to 2. And if I take the root of both sides, I get x minus 3 is equals to plus or minus root 2. So what this tells us is that the x-intercept is either 3 plus root 2 or 3 minus root 2. Okay, and we can verify using the calculator that both of these are actually positive values. So the larger one is 3 plus root 2, and the smaller one is 3 minus root 2. So that's what we have for the sketch of part 1. Now, if we check out part 2, we want to find the largest positive domain such that the graph defines a function fx which has an inverse. So by part 2, just to clarify, okay, this of course means that we want to define a domain such that the function has an inverse function. Okay, so if we take a look at fx right now, we know that it has an inverse, but its inverse is not a function. And the reason for that is for a particular value of y, we can't identify a unique x, right? So in other words, it's not a one-to-one function, okay, and it fails the horizontal line test. So in order for the inverse to be a function, we need a one-to-one function, which means that it's either monotonically increasing or monotonically decreasing. So the largest domain that we can take is x is larger than or equals to 3. Because when x is larger than or equals to 3, we have all of this part, the right part of the parabola, which is just a strictly increasing function. And if we're dealing with a strictly increasing function or a one-to-one function, its inverse is therefore a function. Okay, so the way in which we're going to restrict this for part 2 is we're going to define the domain of the function now to be x is larger than or equals to 3 only. Okay, and this will give us an inverse, which is a function. Now, if we move on, part 3, we want to find this inverse function and state its domain. So in this case, right, we know that the original function is given by y is equals to, so this is part 3, right? Y is equals to x squared minus 6x plus 7. But if we want to find the inverse, we need to swap the y for x and the x for y. Now, using this form is actually not going to be the easiest thing because it will be very difficult once I've swapped the x squared and the x for y squared minus 6y, it's actually not very easy to make y the subject. So this is also part of the reason why in part 1 I chose to complete the square for this expression. In that sense, we've got x minus 3 all squared minus 2. This is a lot easier to manipulate because we can see that if we want to find the inverse, so for inverse, we swap the y for x and the x for y. So we've got x is equals to y minus 3 squared minus 2. And if I rearrange this, we've got x plus 2 is equals to y minus 3 squared. And now in order to find y, I can just take the square root of both sides. So we've got plus or minus root x plus 2 is equals to y minus 3. So y is therefore 3 plus or minus root x plus 2. So we need to decide which branch we need to take. In this particular case, in part 2, we know that since the domain of the function is restricted to be x is larger than or equals to 3, then what that implies is that the range of the inverse is therefore y is greater than or equals to 3. So since the range of the inverse is y is larger than or equals to 3, it makes sense if the equation of the inverse is 3 plus the square root. Okay, so therefore, the inverse function is given by 3 plus the square root of x plus 2. Okay, if we took the other half, 3 minus the root x plus 2, the range of the inverse is not going to be y is larger than or equals to 3. Okay, so that's what we've got for part 3. And now for part 4, we want to state a domain for which the function does not have an inverse function, and we want to give a brief reason for our answer. So we know that in part 1, when we looked at the graph, we restricted the domain of the function to x is larger than or equals to 3 so that the function is 1 to 1. Or in other words, when we have the right half of this parabola, we can see that if I give you a y value, we can identify a unique x, right? But if we consider this parabola as a whole, right, which is a many-to-many function, we can no longer identify a unique x with a particular value of y. So when that happens, we know that the inverse is not a function. So the simplest answer for part 4 is therefore all real values of x, because if we define the function for its natural domain, then we know that it's no longer 1 to 1, and instead it's a many-to-many function. So therefore, the domain which we would choose so that the function does not have an inverse function is x is all real values. And the reason is because for particular values of y, okay, so for particular values of y, there is more than one corresponding value of x. Okay, there's more than one corresponding value of x. Therefore, the function fails the horizontal line test. Function fails the horizontal line test, and its inverse, okay, is not a function, right? So that's essentially what we have for part 4. Now moving on, part 5, we then want to sketch a graph of the inverse in part 2 on the same axis as the given curve. So if we come back to what we have in part 1, okay, remember that we no longer want to deal with the left half of the parabola. Okay, we restricted it so that the domain of the function is x is larger than or equals to 3. So we're going to be dealing purely with the right half of the parabola. So therefore, we want to sketch the inverse of this part. So the inverse of this part, take note, see how the vertex over here starts at 3, negative 2? So if we know that it starts at 3, negative 2, then we know that the inverse is therefore going to start at negative 2, 3. Okay, so this is not drawn to scale. If you guys did it to scale, it's going to look a lot better. Okay, the main reason here is I put this point at 7. But anyways, so if I ignore this part over here, okay, we know that the inverse is just going to be the mirror image of y is equals to fx about the line y is equals to x. And we know that the inverse will meet the original function on the line y is equals to x. So the mirror image is therefore just going to look something like this. Okay, you guys should agree that these two are mirror images of each other about the line y is equals to x. And this point over here, okay, is going to be -2, 3. And you guys can see that it's related to the original vertex of the function. The x and the y values are just swapped. Okay, so that's essentially what we have for the graph of the inverse. Now, lastly, for part 6, we want to hence evaluate the inverse of function 1. Now, there's actually a lot of tricks with this one. A lot of people, after doing some inverse functions, they come along and they go, okay, when I apply the inverse in the function, they cancel each other out, and I'm just going to get the x value that I started off with, which is 1. And in principle, that's okay, because what function 1 is about is like saying, okay, when x is equals to 1, I'm going to get a y value, right? And we call the y value function 1. If I take the inverse of this y value, it's like asking what value of x did I start off with? So of course, I just go backwards and I get 1. But in more complex situations, such as this question, that's actually not going to be the case, because when we looked at part 2, we defined the domain to be x is larger than or equals to 3. So let me just draw this out, roughly speaking, so that we can essentially see what's happening, right? So this is x, this is y, and essentially what we did was the parabola that we've sketched looks something like this. Okay, this is of course not drawn to scale at all. And this is the point 3, -2. And we defined it so that the domain for the function is x is larger than or equals to 3, so that the function actually possesses an inverse that is actually a function, right? So we ignored the left part. So the implication of that is that function 1, x equals to 1, is actually undefined because we don't want the left part of the parabola. Now, one way of getting across a simple case such as this one is because in earlier parts we actually have the equation of both the function and the inverse, we can actually just use the equation to do the work for us, right? What I mean by that is function x we know is given by x squared minus 6x plus 7, and we know that the inverse is given by 3 plus root x plus 2. So if that's the case, we know that function 1 is equals to 1 squared minus 6 times 1 plus 7. So 1 minus 6 plus 7, that's just going to be 2. And now if I want to take the inverse of function 1, right, that's just going to be looking at the inverse of 2. Then that's going to be 3 plus square root of 2 plus 2. 2 plus 2 is 4. Take the square root of 4, that's going to be 2. 3 plus 2 is going to give us 5. So the final answer is therefore 5. Now, in more complex scenarios, sometimes we could be working with pronumerals. So using equations is actually not that easy. So when those times happen, it's much easier to resort to the graph. So what do I mean by that? So we can analyze the situation using the graph. If we take a look at inverse of function 1, so let's say that function 1 is over here, okay, and we know that this point over here is x equals to 1, and we know that this is the y value that we get when x is equals to 1. Now, if I want to take the inverse of function 1, I just want to ask myself, for this particular y value, what value of x do I get? So if I don't want the left part of the parabola, we know that this y value repeats itself on the other side of the parabola over here. Okay, and because the parabola is symmetrical, take note that the axis of symmetry is at x equals to 3. The original point over here is 1, which we don't want, but that allows us to see that the distance of this point away from the axis of symmetry is going to be 2 units, right? So on the parabola, the same y value occurs over here, and that should happen 2 units to the right of the axis of symmetry. So therefore, x equals to 5, which is 2 units to the right of the axis of symmetry, is going to give us exactly the same y value. So therefore, if I want to ask what value of x gives me function of 1, one answer, sure, that's going to be 1. But if we don't want this, we know that the second answer is going to occur at x equals to 5, because x equals to 5 also gives us exactly the same y value right here, right? Which is function 1. So therefore, the solution to this is x equals to 5, whether we do it by algebra or whether we do it graphically. Okay, so that being said, this concludes example 4.